The 737 airplane is powered by two CFM56-7 engines. The engine is an axial flow turbofan with two rotors. The N1 rotor has a fan, a low-pressure compressor section, and a low-pressure turbine section. The N2 rotor has a high-pressure compressor section and a high-pressure turbine section. The N2 shaft turns the accessory gearbox. The accessory gearbox drives the integrated drive generator, the oil pumps, the fuel pumps, and the hydraulic pump. Air passes through the fan. Some of the air goes through the compressor for combustion. A large part of the air goes through the duct to provide most of the thrust. Next is an overview of the engine fuel system. The fuel system supplies fuel from the fuel tanks. The fuel goes through the first stage engine fuel pump. The fuel is heated by the IDG oil cooler and the fuel oil heat exchanger. The fuel then goes through a filter that removes solid contaminants. After a second stage pump and a second filter, the fuel goes to the hydromechanical unit, or HMU. Here the electronic engine control, or EEC, adjusts the fuel flow. Part of the fuel goes to the combustion chamber and the unused fuel returns to the fuel pump. Next is an overview of the engine oil system. The oil pump pressurizes the oil from the tank. The oil goes through an oil filter and continues to the engine bearings and accessory gearbox. The oil temperature and pressure sensors are located here. The scavenge pumps collect the oil from the engine. The oil then goes through an oil scavenge filter to remove contaminants. The oil goes through the fuel oil heat exchanger before it returns to the tank. Each engine has flight deck controls. You manually set power with the thrust levers, or automatically with the auto throttle system. Each engine is controlled by an EEC. The EEC uses the thrust lever position and environmental inputs to control the engine's thrust. The engine indications are shown on the upper and lower display units. The primary and secondary engine indications are shown on the upper and lower display units. If a DU fails, the engine indications automatically move to the other DU in a compact engine display. N1 and EGT are the primary engine indications. Fuel flow is displayed full-time on the upper DU below the primary engine indicators. N2 fuel flow, oil pressure, oil temperature, oil quantity, and engine vibration are the secondary engine indications. They are discussed in a different lesson. There are some differences in the primary engine indications. The pointers show the related digital readouts position on the indicator. The normal range is white. Move the thrust levers forward and look at the N1 indications. The white commanded sector arc outside the dial shows the difference between commanded N1 and actual N1. Move the thrust levers to idle and look at the N1 indications. The reference N1 bug and reference N1 readout are shown with the N1 indications. They are discussed in a different lesson. A red EGT start limit line is shown during engine starts. The start limit line is discussed in a different lesson. Let's look at the fuel indications differences. The type of information that the digital readout and related pointer show still depends on the position of the fuel flow switch on the engine display control panel. In the rate position, the digital readout shows the rate of fuel flow. Momentarily move the fuel flow switch to used. The readout changes to the current fuel used since the last reset. After 10 seconds, the display goes back to fuel flow. Momentarily move the switch to reset. In the reset position, the readout first shows the fuel used, then decreases to 0, and then goes back to fuel flow. We will now look at new indications for non-normal conditions. If an N1, N2, or EGT value goes above an operating limit, the dial, readout, and box change color. In this example, the EGT is more than the maximum continuous limit. The indication becomes amber. If the temperature goes above the maximum operating limit, the indication becomes red. When the temperature decreases below the limit, the indication changes back to white. If an N1, N2, or EGT in-flight exceedance occurs, the box becomes red after engine shutdown on the ground. In this example, the EGT had an in-flight exceedance. An amber engine fail alert is shown if the related engine's N2 decreases below a stabilized idle of approximately 50%, and the engine start lever is in the idle position. The alert is removed if N2 increases above stabilized idle, or the start lever is moved to cutoff, or the engine fire warning switch is pulled. A magenta crossbleed start indication shows if a crossbleed start is necessary for an in-flight engine start. The secondary engine indications are oil pressure, oil temperature, oil quantity, and the airborne vibration monitor system. The oil pressure and oil temperature indications are vertical indicators with moving pointers. The oil pressure indication is shown in PSI. Oil temperature is measured in degrees Celsius. The oil quantity digital readout shows oil quantity in quarts. Low oil quantity is displayed by reverse video and a low message next to the quantity indicator. The normal operating range for oil pressure and temperature is shown in white. The operating limit for both is shown here by a red band. When the oil temperature enters the caution range, the display changes to amber. The size of the oil pressure caution range is a function of the N2 RPM. The amber band increases in size as N2 increases from 65% to its red line. When N2 is below 65%, there is no amber band. The Airborne Vibration Monitoring System, or AVM, monitors engine vibration levels to track rotor imbalance. The indicator displays units of vibration. It shows the higher engine vibration level of N1 or N2. High vibration is displayed by reverse video, indicated by the AVM above 4.0 units. Let's now look at some non-normal indications. The first indication is a low oil pressure condition. Since the output pressure of the oil pump is unregulated and varies with engine speed, engine oil pressure may go into the amber band and the pointer turns amber. If the oil pressure goes into the amber band with takeoff power set, do not take off. Oil pressure in the amber band is not normal at high thrust settings. If the pressure continues to decrease and reaches the red limit, the display end pointer turns red and the low oil pressure alert illuminates. The pressure is now too low for continued engine operation and the engine must be shut down. Next, let's look at a high oil temperature condition. The oil temperature is measured prior to the oil entering the gearbox. If the oil temperature goes into the amber range, the pointer and displays turn amber. With temperature in the amber range, you can operate an engine for 45 minutes before an engine shutdown is required. If the temperature continues to increase and reaches the red line limit, the pointer and display turns red. The oil temperature is now above the operating limit for continued engine operation, and that engine must be shut down. There is one other engine alert associated with the engine oil system: the oil filter bypass. The scavenge filter has a bypass feature with pressure sensors at the inlet and at the outlet. If the filter becomes contaminated, the oil filter bypass alert illuminates to show a bypass of the filter can possibly occur. If the oil filter bypass alert remains illuminated after thrust reduction, that engine must be shut down. When the low oil pressure and oil filter bypass alerts display, they flash for 10 seconds, then stay steady until the related condition no longer exists. The flashing indication is inhibited during takeoff. When inhibited, the alert immediately illuminates steady. In this example, there is a low oil condition during takeoff roll. The reference N1 bug, reference N1 readout, and thrust mode display are above the N1 indications. The reference N1 bug and reference N1 readout are controlled by the N1 set selectors on the engine display control panel. The outer knob has 4 positions, both auto, 1 and 2. In the auto position, the FMC automatically sets only the reference N1 bug. The reference N1 readout is blank. In the 1, 2, or both position, the reference N1 bug and readout are controlled by the inner knob. In this example, the outer knob is in the 1 position In this example, the outer knob is in the 1 position and the N1 bug and readout appear above only the number 1 N1 indication. Now set both reference N1 readouts and bugs to 86.8. First, turn the outer knob to both. Next, turn and hold the inner knob until the readout and related bug read 86.8. Next, let's look at the thrust mode display. The thrust mode display is calculated by the FMC. The thrust mode display is the active N1 limit reference mode for autothrottle and manual thrust control. If the FMC calculations become invalid, the autothrottle computer calculates a degraded N1 limit for the affected engine or engines, and the autothrottle limit indication illuminates. These are the thrust mode displays available for the different phases of flight. Touch each mode to see its definition. Each engine is monitored and controlled by an electronic engine control, or EEC. The EEC uses thrust lever position and flight conditions to control forward thrust, reverse thrust, and idle. The EEC supplies N1 and N2 redline protection. If N1 or N2 goes near the red line, the EEC commands a decrease in fuel flow. However, you must monitor the EGT limit because the EEC does not supply EGT redline protection. The controls for the EECs are on the aft overhead panel. Both EEC switches are guarded and should be in the on position for pre-flight and during normal operations. The EECs have 2 modes of operation, normal and alternate. Let's first look at the normal mode. When the EEC switch is in the normal position, the white on light is in view. In the normal mode, the EEC calculates a commanded N1 value based on the thrust lever position and flight conditions. The EEC compares commanded N1 to actual N1 and adjusts fuel flow to change engine speed until actual N1 equals commanded N1. The EEC can operate in one of 2 alternate modes, soft or hard. If the necessary normal mode inputs are not available to the EEC, the EEC changes to the soft alternate mode automatically. In this example, an input to the number 1 engine EEC is gone. The alternate light, the engine system annunciator, and master caution lights illuminate. This mode is the soft alternate mode because the EEC switch stays in the on position and the alternate light has illuminated. The EEC now uses the thrust lever position and locks in the current ambient conditions to calculate maximum N1 data. The EEC then internally locks in this calculated maximum N1 to prevent uncommanded thrust changes. The hard alternate mode is entered if the thrust lever is moved to idle or if alternate is set with the EEC switch. The hard alternate mode is also set with the EEC switches. You can manually set the alternate mode when you are in the normal mode or the soft alternate mode. To control thrust in the hard alternate mode, the EEC uses thrust lever position with internal data. The hard alternate mode removes the parameters that were locked in when the EEC went from normal mode to soft alternate mode. When the alternate modes are removed, thrust lever movement can occur. Before you set the hard alternate mode, move the thrust levers to mid position, and if the auto throttle is engaged, disengage it. This prevents the engines from exceeding the thrust limits and allows the thrust levers to remain manually positioned. Set the alternate mode for engine number 1. First, lift the engine number 1 EEC switch guard. Next, push the EEC switch. The on light goes out of view and the alternate light stays illuminated. The EEC is in the hard alternate mode. If one EEC is in the alternate mode, it is necessary to put the other EEC in the alternate mode. This makes sure the two engines operate in the same mode and there is no thrust lever stagger. Next, we will discuss engine idle. 3 different idle modes are available to the EEC. They are ground minimum, flight minimum, and approach. The EEC selects ground minimum idle for ground operations. Flight minimum idle for most phases of flight, and approach idle in flight if flaps are in landing configuration or engine anti-ice is selected for either engine, or there is a fault which prevents the EEC from receiving flap or anti-ice signals and the aircraft is below 15,000 feet. Approach idle improves engine acceleration time for go-around. Approach idle is maintained for 5 seconds after touchdown, then ground minimum idle is selected. Finally, we'll discuss the engine control lights. The engine control light illuminates if faults are detected by the EEC that require maintenance. The light operates only when the airplane is on the ground. The master caution and engine system annunciator lights also illuminate. Reset the master caution system. If either engine control lights illuminate, the airplane cannot be dispatched.